Cool. All right. Import pandas, NumPy. All right. So in a nutshell, the maximum likelihood estimation is a method that we use um, when we're estimating the parameters of a statistical model. And so you want to find the parameter that maximizes the likelihood of the observed data. So what does all that mean? We need to kind of go back and um, look at some of the theory behind it. You have the likelihood function. Let's write that down. Likelihood function. And so this measures how likely are you to observe any given data under a different parameter um, inside the model. So when you have a parameter theta, like so, then the likelihood is defined as follows. So you have L of theta is equal to the probability of the data that you have given that theta, like so. Okay, actually misspelled likelihood. So you have theta, that's your parameter. And the likelihood is you take the function L of theta of that parameter, the probability of data given that parameter. So that's your likelihood function conceptually. And then what you want to do is define your model, right? That's step two. What is the assumption? So we have a set of data points. And let's say we want to estimate this parameter or sets of thetas. So we're working with the normal distribution, and a lot of times you will be working with the normal distribution. That's the underlying assumption. You have your mean mu and your standard deviation sigma, and these values will generate some data, d or data, as we spelled it out above. So theoretically, you're defining the model and you're basing it on the normal distribution. You're making what we call a Gaussian assumption. Gaussian assumption. Okay. And yeah, it's well, let's make that into a comment actually. All right. So then after you define the model, you want to define the likelihood function. What is it? So in a normal distribution, you can have so many different data points. For example, x sub 1, x sub 2, x sub 3, comma, and so on and so forth. So something like that. Okay. All the way through x sub n. Those are your data points. Okay. So when we're defining the likelihood function, the formula for this, let's label that. Is as follows. And let's make this one stand out. You have those parameters based on the normal distribution, the mean and the standard deviation. That is exactly right. So mu, comma, sigma, that's what this function takes in. And this might be a bit tricky to write out, as I haven't done this one in a while in LaTeX. This, no. Or actually, here we go. There we go, perfect. we have the product. So this would be the from I equals 1, like so, to n, something like that. So as we're building out this function, and you can look this up, it should be in your textbook. We have 1, so that's multiplied by 1 over the standard, 1 over the square root of 2 pi sigma squared. So it's a lot to write at one time. Is that right? Yeah, just gotta take the square root of that. Yeah, so we just want to take the square root of this expression. That's inside the denominator. SQRT, that was correct. And then another pair of curly braces, so it's doubled. So I think we need one more. There we go. There we go. Finally. But essentially there's an exponential and you're multiplying it, just finish it then, by the difference in the means divided by the 2 times this variance. So that's your normal distribution. So again, your numerator is as follows. Your denominator is 2 squared. There we go. Just forgot the closing parentheses. So here's the formula for the likelihood function. So we can work this out algebraically or mathematically, but essentially you're going to use the log likelihood. So you reverse out the operations for the exponential. And because logarithms are monotonic functions, they're either decreasing or increasing, maximizing this likelihood would be this, what we're seeing here would be as if we converted this to log form. That's just the math behind it. But essentially, after we've read in our requisite libraries, I'm not going to save this file just yet. We have pandas, we have NumPy. Let's also import from SciPy stats. We need to generate some sample data. And I think we have, yeah, minimize. That's what we want. So SciPy optimize, minimize. All right. So to import that, we'll say from SciPy dot optimize import minimize. Run that again. And let's proceed to generate some sample data as follows. The best way to do this whenever you're generating sample data is to lock in a random seed for reproducibility. We're going to specify numpy.random.seed. Let's give it 0, for example. And to generate the data, we'll assign it to a variable called data. And this will be a random normal distribution, random.normal. We'll have this location, set it equal to 5, scale it to 2, and it'll be of size 1000. Before we move any further, let's go to this definition of random normal distribution. In the VS Code, what's really cool is you can right-click on the function and go straight to definition. So we can inspect some of these inputs, or we can also go to the documentation straight off of the NumPy library and inspect what we're passing in. So loc is your mean, that's the center of your distribution. Scale is your standard deviation. Size is the shape. So we have our mean of 5, standard deviation of 2, and I misspelled size. It should be this way, size equals 1000. That's our data. It's locked in with random state or random seed 0. And so now that we have our data, what does it look like? For example, let's run it. It's a NumPy array. See if we can put this into a frame. So it's a NumPy array of all these values. We can convert it to a data frame if we want, but that won't be necessary at this stage. So we'll keep it nested inside this NumPy array. And we want to use this data to define the negative log likelihood function. And so because we have minimize in SciPy, this function, what does it do? Let's have a look. So it takes in fun, which is callable, that's the function to be minimized. X0, that's your initial guess. An array of real elements of size n. N is the number of independent variables. And args is an optional argument, and so is method. So there are others as well, as you can see here from the inputs. So we'll keep that handy for just a moment. But we'll use that potentially in the following operation. We're going to create a function to define the negative log likelihood. We'll call it neg underscore log likelihood. So we'll have inputs. We know we're going to need data. And we'll indent. We'll have our standard deviation and our mean. So mu and sigma is equal to our parameters. And so because we have that, now we need to put this inside as our input. And n will be the length of our data. So that's the sample size. And the log likelihood would be equal to minus, because we're looking at the negative log likelihood, n divided by 2 times, we're just following the function. So I was going to show you how to derive it up top theoretically, but what you're going to see now is done Pythonically. So if you're following this from the textbook or whatever resource you use for formulas in stats, to define the log likelihood, we have minus n, so that's the length of our data, divided by 2 times the log. We're using this function from NumPy. 2 times the pi minus n times the log of sigma. And then we subtract this from 1, divide that by 2 times, might have messed up the parentheses here. Let me think about this one for a sec. So we have this sigma minus 1, and 1 divided by, we need to open up another parentheses here, 2 times sigma squared, like so. And so then we're going to take this and multiply it by the sum. Notice how we're using NumPy for most of these operations of the data minus mu. We're just plugging this straight into Python as it would be written mathematically. And we need to return, to finish off this function, the negative of this, the log likelihood, because we are defining the negative log likelihood function. So let's go ahead and run that. I have an automatic linter, so it's going to convert it to PEP 8 standards anyway. And so to find the maximum likelihood estimate, we're going to finally use this minimize function. But before we can do that, we need to set up our initial guess. And that can just be a list of values between 0 and 1 in terms of probability. That's our initial guess for mu and sigma. And the result of all that would be to use the minimize function to find the maximum likelihood estimate, which takes in the negative log likelihood, our initial guess, and what else? We can specify the arguments as data. But before we can finish this off, we want to get the average mu of the maximum likelihood estimate, as well as the sigma of the maximum likelihood estimate, because we have the original. And so this would be equal to the result, which is set up here. Let's go ahead and run that. There's probably a mistake in somewhere. Int object is not callable. And that stems from this piece here. I think I missed a comma when I set up the function. Invalid value encountered in log. So we have minus n times the log of sigma, 2 times sigma squared, and the sum multiplied by the sum of data. But there is a runtime warning, so minus n np log sigma. Let's see what happens. Maybe there's an issue with some of these parameters. Let's go back to the documentation. So we have our arguments. It's an empty function. It's a tuple. It's an optional pair of extra arguments passed to the objective function and its derivatives. So, okay, we can pass that in as data, I suppose. And bounds, if there is such an argument here, let's see if they have that here, bounds. Yes, they do. So we can add a tuple of bounds, I suppose. And yeah, I think we can give this one another shot. So we have bounds and arguments. So yes, data, and see what happens if we don't pass anything here. Then our bounds will be a list of tuples. So none, none, and then a very small number or something like this and that. And we'll have to close out this list. And interesting. Invalid syntax. Oh, I have an extra value here. Still in, oh, so this needs a comma. And our bounds. Oh, yes, this is missing a comma. Of course. But still, what's the issue? Too many values to unpack, expected to. There we go. Okay, finally. Was worth the juice was worth the squeeze, I suppose. We can print these out like this. So we'll use an F string to say the estimated mu is as follows. That's our mu MLE. And then same thing for the estimated sigma. And so that is the maximum likelihood estimation. It was a bit tricky, it was a bit rocky, but we got there. And you can always reproduce this after the recording.